Okay, 5.2 critical points. We're going to start off with the extreme value theorem, which is one of the big theorems of calculus. So if a function f is continuous on the closed interval ab, let me sketch a possibility. Maybe something like this. This is continuous. It's closed because it includes the endpoints. Let me do another one. How about something like this? This is also closed because it has the endpoints. It's continuous. It's connected. It's not differentiable, but that's not a requirement of this theorem. Okay, if a function f is continuous on the closed interval ab, then f has at least one maximum and minimum value. Okay, so at least one maximum. So the first function looks like it has a maximum value right around here. That's the absolute highest point. For the second function, the maximum value would occur somewhere on this segment, line segment, and there's an infinite number of maximum values. So it says at least one, but there could be more than one. Okay, and at least one minimum. So for the first function, there is one minimum that occurs around here. For the second function, assuming those two endpoints are even, there are two minimums. So if it's closed and continuous, there has to be at least one maximum and one minimum. Okay, vocabulary. Absolute global extrema is the highest lowest point on the interval. Okay, some things, extrema just means extreme points. It's the plural for extreme, or it can be maximum or minimum. It's the extreme highest or extreme lowest. Local relative extrema is the local or relative extreme points. It's the highest, lowest points in an area near the point. So it doesn't have to be the absolute highest or lowest, but it's the lowest or highest in that little area. So for example, when we're going to identify the extreme values, which is their y value, and their location, which is their x value, and their type, whether they're absolute or relative. Let's start with absolute extrema because they're easiest. Okay, so let's look for an absolute minimum first. What is the absolute lowest point on this graph? The absolute lowest point looks like it's this one. So I'm going to say there's an absolute minimum. The value of that point is -2. The absolute minimum value is -2. The location is the x value. So that occurs at x equals -5. -1, 2, 3, 4, 5. Let's look for the absolute maximum value. Okay, what do we think? It seems like it should be here, but there's no point there, so there's no defined value there. So I can guess that the absolute maximum value is very close to 10, and it approaches 10, but there's no actual point there. So there is no absolute maximum on this graph because there's no defined value there. If you're thinking, wait, you just told me there's at least one maximum or minimum value, that's only true if this is continuous, which it's not, and if it's a closed interval, which it's also not because it's not including the endpoints. Okay, let's look for the relative extrema or the local extrema. Okay, I'm just going to go from left to right. Okay, if I start on the left, this point looks like it's higher than the points on the right, but it's an open circle, so it's not defined. So this does not count as a relative maximum. If it were a closed circle, it's an optional circle to include because it is higher than the points on the right. It is not higher than the points on the left because there's no points on the left. So depending on your textbook, they would or would not include it. I'm fine with either way. So let's continue on this graph. I'm going down, 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 down. I go down to here and then I go back up. So this is some kind of minimum. So this is a relative minimum because it's lower than the points on the left and right. So relative min or local minimum. The value of the relative minimum is -2, and that occurs at x equals -5. And just because something's an absolute extrema doesn't mean it's not also a relative extrema. Okay, let's continue here. This looks like it's high, but it's open circle, so it doesn't count. Let's go up to this point up here. Now, if I go to this point up here, this is a defined value. Does it look like it's higher or lower than the points to the left and right of it? Well, it's definitely higher than the points on the right. It's also higher than the points on the left, so that is considered a relative maximum. The value of that point, the y value, is 8, and that occurs at x equals 0. Okay, let's keep going. Okay, go down here. This looks like a relative minimum. It's an open circle, so there's no defined value there. If it were a closed circle, it would count. Okay, so I'm going to go to this circle up here, which is defined. Now, looking at this point, is it a relative maximum or minimum? It's a relative maximum because it's higher than the points on the left and right of it. So that is considered a relative maximum. The actual value there is here. So that's of 8. And that occurs at x equals 5, 6. X equals 6. Okay, let's keep going along this graph. Okay, again, if this were colored in, it would be a relative maximum, but now we're going to this defined value here. This value is lower than the points on left and right. So that's considered a relative minimum. The y value here is 5, and that occurs at x equals 9. Let's keep going on this graph. When I get down to here, that is lower than the points on the left and right, so that's a relative minimum. The value is 2, and that occurs at x equals 5, 10, 14. Okay, now let's go up here. Okay, and this looks like it could be a controversial relative max, but it's not, it's an open circle, so it's not defined, so it's irrelevant. Okay, so we've listed all our relative extrema and our absolute extrema, and the relative extrema is typically way more than the absolute. Okay, now let's define critical points. Critical points are points in the domain that have the possibility of being a maximum or minimum. Okay, so on the graph on the right, that's going to be here, 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 and here. They occur when f prime changes sign from positive to negative or vice versa. The way we calculate them is if I drew the tangent line at each of these points. I drew the tangent line here, it equals 0. If I drew the tangent line here, it equals 0. If I drew the tangent line here, it equals 0. Here is 0 here. At this is a corner, so f prime does not exist, but it is a critical point there. So critical points, the way you find critical points is you set f prime of x equal to 0, or f prime of x does not exist, and then you find x. And then those x values are your critical points, or the points that have the possibility of being a maximum or minimum. Okay, so let's find all the critical points. To find the critical points, we said f prime of x equal to 0, or see where f prime of x doesn't exist. So the first thing is find f prime of x. Okay, let me bring down the 3. 1/3 of 3 is 1, so this is x squared minus 9. Okay, now I need to set this equal to 0. Okay, and I get x equals plus or minus 3 as 2 critical points, because they both make f prime of x equals 0. Is this undefined anywhere? No, it's a parabola. It's continuous everywhere. There's no undefined values. Okay, let's try B. Find the critical points. First thing is I need the derivative, so let's do the derivative. Do we want to do quotient? No, let's rewrite this as x squared minus 4 to the negative 2. If you would like to do quotient rule, you're going to get the same answer anyways. Okay, but I want to do power rule, so let me bring down negative 2. X squared minus 4, I'm going to lower it to the negative third. And since the parentheses has an interesting function, I'm going to multiply by the derivative of the inner function because of the chain rule. So I'm going to get this. Okay, let's rewrite this. What is that? Negative 4x over x squared minus 4 to the third. Okay, to find the critical numbers, I want to see when g prime of x equals 0 or when g prime of x does not exist. Okay, if I set this whole thing equal to 0, over time, the x squared minus 4 to the third to the right. So I get negative 4x equals 0, which means I get x equals 0. Now I just need to verify that this gives me a defined value. So if I plug in 0 here, 0 minus 4 is negative 4 squared is 16. So this is 1 over 16. So x equals 0 is a critical point. Okay. I also need to consider when g prime of x doesn't exist. Okay, since this is a fraction, when does g prime of x not exist? When the bottom is equal to 0. Okay, so let's set the bottom equal to 0. Okay, I'm going to third root it so I get x squared minus 4 equals 0. And then if I solve this, I'm going to get x equals plus or minus 2. Okay, now let me just verify that these are correct values for this function or valid points, because critical points are points in the domain. So if I go back up, if I plug in 2, 2 squared is 4, 4 minus 4 is 0. So I'm going to have 1 divided by 0, which doesn't work. If I do negative 2 squared, I get positive 4, and then I minus 4, which also doesn't equal 0. So I solved it correctly, and I did need to consider this point here. But these do not count as critical points. And the reason is because g of 2 and g of negative 2 are not defined on the graph of g. So there's only one critical point, it's at x equals 0, but you do have to check for g prime of x being g prime not exist, or g prime of x does not exist, to see if there are additional critical points, because there often are.